Hello, this is Tom from anti-proton.com, and I wanted to talk to you today about, proper science, radiation in the rain, and maybe the betterment of what you might call amateur science on places like YouTube. For starters, there are lots of people doing lots of things on YouTube with cameras and Geiger counters and testing rain and all these other sorts of things. And that's great, by the way, too. Amateur science is not only wonderful, it's how a lot of amazing discoveries have been made. Not everybody who makes a discovery has a PhD. Now let me start by saying something right off the bat. This is kind of important. Who am I? I'm Tom. I do not have a degree in physics. I do not have a degree, well, I do have a degree in science in so much as I have a computer science degree. But I do not have a degree in classical science, chemistry, biology, physics, those sorts of things. That being said, regardless of how long I've studied science and physics, and I've studied them a lot, and when I've tested in colleges, I test at bachelor's degree levels usually, the little acceptance things that they do. I did a test for that for master's degree entrance. But regardless of that fact, I am an amateur. Alright, that is a hobbyist, that is an enthusiast. Meaning a person who is not classically trained. As a result of that, and as a result of many of the other people who exist on YouTube doing videos and stuff, or who have websites, I actually have a website, YouTube is a secondary thing, you should always take what we say with a grain of salt. Check to see that we back up things that we say. Check to see that we practice proper science. And let me start off now by talking about what proper science is. I've seen a lot of improper science of late. Before that, I should say that it's always true that people are people. They are going to make mistakes. They are going to they're going to sometimes not practice what they preach. I am guilty of this. I remember a time when I took my Geiger counter and I was examining a person who had technetium-99 treatment. And I recall, after now looking at the video, at the time I was sort of spooked by the tremendous radiation coming off of her. But my Geiger counter was registering in microsieverts per hour, which was very wrong. You shouldn't have been using microsieverts per hour. I wasn't calibrated to the source, which was technetium-99 in this case, minus background. And of course, I was yelling out loud counts per minute. The reason I was doing that is because I knew the conversion off the top of my head from what it showed as the energy, which I didn't know anyway, to what was shown in the Geiger counter. The whole thing was done inappropriately. Now, to my defense, I was also panicking at the time too, because I was getting, like, x-rays by standing in front of this lady, basically. But regardless, people are prone, every person is prone, to the possibility of doing the wrong thing. You see sometimes when cops do the wrong thing, you see sometimes when doctors do something and somebody gets hurt, people do the wrong thing. But that being said, you should also always try to do it the right way. I personally, as best as I can, try to do science as correctly as I can. And many of you have pointed out a few times when I haven't done something correctly, although I would like to point out that I've never wholly scammed anybody or anything like that, of course. I always try to do the best I can. Let me talk to you for a moment about what correct science is. Correct science is the attempt to explain things, to understand our natural phenomenon around us. When one practices science, they should never be too set on a specific outcome. Take this little beaker, for example. This beaker, what is it? Looks like a 100 milliliter beaker. Yep, 100 milliliter beaker. It's got the slime stuff in it. It's actually seaweed, for example, and I'm dissolving it down into this solution so I can test it with gamma spectroscopy. If I took this seaweed and put it into my gamma spectrometer over there and ran it, and then I kept changing the results. In fact, if I went so far as to go into my calibration on my machine and change it, because I saw an energy here, and I was expecting to find, let's say, iodine 133 or whatnot. If I saw an energy spike here, but I figured that iodine should be here, and if I adjusted my settings to match it, because it looked close, if I did that purposefully and then stated matter-of-factly that's what it was, if I did 100 tests of the rain outside and found no radiation in any one of them, but in one of them I found a slightly elevated reading and I threw out the others and went for that one, that would be wrong. That's the act of trying to match your results with your expectations. When you are very much bent on one result and you won't accept others, that's not very proper science. The only exclusion to this would be when you're accepting the norm versus the deviation. Meaning, if I go outside and I scan and I get normal results in the air, for example, I'm not getting radiation, for example, not any major amount, and I publish something telling you that for the last month I've been testing and I haven't gotten results, but then the next day I publish one that says I do have a result, it's a little different because those earlier results are the norm. They're what's expected, and I do publish that I found them, but I don't have to publish them individually because they're the expected result. I can publish the results of a group of them, whereas the variance, the big one, I can publish independently. I see a lot of people getting on YouTube and they wipe a car, for example, and then they claim they found 10,000 counts per minute off of their car, and that's nice and all, but what are their readings normally? What are their readings around their area? Why aren't these things taken into account? They have to be. Proper science requires documentation, examination. They have a hypothesis. Their hypothesis is their, how do you put it? Hypothesis is kind of like what you believe something to be based on the evidence. It's called an antecedent in formal logic, more or less. Basically put, A, if conditions for A are true, then they imply that B is true. If I turn on the heat, the room should get warmer. Now, one should always base everything on the first part, the antecedent, not the consequent, which is the second part. For if the room becomes warmer, it does not necessarily mean that A was true, that the heat was cut on. It could have been a warm day. When you have a hypothesis that radiation is in the air, presumably from Fukushima, that's the current red herring for all of this, but let's just say that there's radiation in the air, I will detect, when there's radiation in the air, and we're saying that it is from Fukushima, and when I go out to my car and wipe it with a paper towel, I detect high amounts of radiation as a result of it, then it is improper to say that because I detected high amounts of radiation off my car, presumably with a paper towel, that it is necessarily from Japan. This is what's called a logical fallacy. You're affirming the consequent. And that's... I'm trying to remember what the actual Latin term is for that. I can't recall it off the top of my head. It's modus pono something or other. But anyhow, it's a logical fallacy. Science should be about the studying of everything and reporting what you find, good or bad. Yes, I know, when you're testing for the radiation outside, you're wanting to find something. And that's always been a problem with science, and all scientists will admit it usually. The urge to find something is strong. But you must also report when you don't find something. Now, that being said, all of that being said, I wanted to point out one other thing. There are people who believe and follow whatever they're told. If the establishment states, there is nothing to be afraid of, nothing to worry about, such and such event, nothing happened, it's all okay, and you just, yes sir, we believe you. When you do that, you're like a sheep. I'm sure I've offended some people, but keep in mind if you're offended, that would mean you have to be part of that group, so I apologize to you if you're offended, and I hope you seek something. But anyway, the point is, if you follow every little thing you're told and you never question anything, that is bad. But on the other side, and a lot of people seem to misunderstand this, on the other side, if you believe that everything you were ever told is a lie and false, and when anybody in your establishment, that's government, that's scientists, that's universities, if you believe that everything they say is wrong, it is all a conspiracy, and everything is designed to trick you, you're in the opposite side of that same spectrum. That is also bad. They're both extremes. The middle is a skeptical person who has healthy skepticism. The skepticism of that person is proportionate to the claim. For example, if I told you it's winter time, it's November, but it's 70 degrees outside, you could take that with skepticism. It probably shouldn't be, but it's possible. In Virginia, the state where I live in the United States, 70 degrees, off the top of my head, I think it probably could occur in November. You'd want to look at historical data to see if that's true or not, but that's within the realm of believability. Be skeptical. But you almost could accept that one. Now, if I told you that standing right outside of my window right now is a 500-foot tall living Elvis, it's not a balloon, it's the real thing. He's standing there right now being the king. That might not be within the realm of believability. Who knows? Maybe the laws of physics broke down and the universe is dissolving before us and that actually happened, but probably not. It's most likely that I'm just, cuckoo. So, take things into believability and have a healthy skepticism for everything anyone says. Now, moving past that for a moment, let's move into more accurate tests of rainwater. And let me show you what I now have. The new toy. Alrighty, folks. This Geiger counter is sitting on top of a piece of uranium. It's not really registering very much, though. I wonder why. Could it be lead? Let's put it around on the other side where the lead isn't. There we go. I have bought lead bricks, many lead bricks, in an effort to test rain samples more accurately, with proper science. Now, let's take our college ring off, and let's put a rubber glove on. I'm probably being overcautious with lead, but you never know. Lead can be deadly. Each one of these little lead bars that I purchased here, they have been spread with polyurethane. They've been sprayed, I say spread, they've been sprayed with polyurethane. Polyurethane protects them and seals them, meaning I probably don't need this glove. I probably don't have any, see, I don't even have any lead dust on my hand. When I picked these up before I put the polyurethane on them, I had lots of lead dust. Now, I've been working on various methods of putting the lead bricks around my unit. Now, to make a proper lead castle, of course, we'd have to do something about this little slitty area in here, but my point is not to make the world's greatest lead castle. It's just to, it's just to do a relatively decent job of shielding from radiation. And if I put enough of these up, I can block out my background radiation. This isn't the world's most sensitive Geiger counter, of course. But if I put some lead here, and I put the uranium sample on top of it, now it's going to drop pretty quickly. Why? Because I have an entire blockade of lead. Not a thing. And this is what I'm going to be doing. The goal here is to fully encase, entomb if you will, my detector. I have 4 more boxes of lead coming, so there'll be one here, and one there. This should be enough, plus the huge clump of lead I put here. See this aluminum piece right here? It's about the same as this 1-inch block of lead. These are sheets of lead that I rolled up. Around the outside is a skirt of lead. I know the aluminum gives it kind of a ghetto feel, and detracts from proper science, so to speak, because it doesn't look so proper. But realistically speaking, these are plates of lead underneath here. And the aluminum is very useful because it has a very low proton count, so it's capable of deflecting and reducing the energy of beta particles without causing very much Bremsstrahlung radiation, which is secondary radiation. Here, let me move the lead pieces out of the way for a second. The little tiny ingots. Even though they're probably safe, I want to hold them like that. Let me open up on my computer. There's my glove. Let me open up on my computer and show you an example of what I mean. My background tests. Okay. For background tests, this is the kind of background radiation I get with no shielding whatsoever, as soon as it loads. Okay. Let's increase the... Oops. There. Do you see what I get with no shields? Look at all that. This right here is what clouds it and makes it hard for me to test rainwater. This is just background radiation that has no bearing whatsoever on my actual samples. However, let's see here. There we go. Here is what I look like with my new shields. So, old, new, old, new. And I don't even have all of the lead in place yet. This is what it looked like without even any of these bricks. That's just with the new shielding around the top. Around the top, it looks like this. Oops, let me change this pixel size so that you can see more clearly. Now let me smooth the data. And now let me smooth the data on the other one. Okay, so this right here, see that I got rid of most of the crap here. This right here is background with no shielding. This is background with shielding. Notice the difference. Once the shielding is fully in place, this should almost disappear. The point of this is that I can more accurately test rain samples. Now, I have been testing rain samples. Well, I've been testing rain samples since the Fukushima event occurred, and I've detected almost nothing. Almost nothing. I live in Virginia, so I'm not going to detect as much as others, but if they're able to detect 20,000 counts a minute, I'm not really sure why I wouldn't be able to detect at least a few. And I'm getting relatively decent peaks on all my other samples I put into the device, so I'm not really sure why it is that other people with Geiger counters that are hundreds of times less sensitive than this unit seem to be able to detect so much more than my unit can, when I know it works perfectly because it calibrates beautifully with a sample. I've been testing rainwater like crazy and I don't get anything out of it. Now, I'm hoping that this coming Monday or Tuesday we're going to have a rainstorm. And next time that we have a rainstorm, I'm going to throw it inside the detector, even if I don't have all of my lead on yet. Because if there are thousands of counts per minute, this should show up in here beautifully. This software is capable of doing a, where is it? It's currently set to a pulse height analysis. But it can do a I think it's an MCS internal. That's the setting I'm setting it to. And what it would do then is it would do counts versus time, and you get a beautiful curvature right here to show radon. And in fact, you'd actually be able to determine that that's actually what that was. The problem when people use Geiger counters and do timed curvatures like that is that you're only going to notice something when it's very pronounced. Now, if it is very pronounced, I've seen some people that have a beautiful curve like this from their timed Geiger counter samples. Those are perfectly acceptable. And they show a radon decay curve pretty well, which of course is what most people are detecting right now with radiation. It's not usually Fukushima radiation. Fukushima radiation does exist, don't get me wrong. It fell across us. There were 3 meltdowns, and even though it was less was released than Chernobyl, it's still pretty bad. It was released over less was released over a broader area. That's a better way to look at it. And it should also be noted that there have been well over 500 nuclear explosions above ground, and, well, all that radiation's out there too. So anyhow, this has been Tom from anti-proton.com. Please stand by. In the next couple of days, you will be getting radiation readings from rain, from me, from an actual working gamma spectroscopic device, a gamma spectrometer, and its name is Nekonome. I believe I'm pronouncing that right. I've been corrected by a friend of mine living in Japan who says that Japanese people would have absolutely no idea what I was saying if I said Nikonami, which is apparently wrong. And to correct myself, I will now call this unit Nekonome. Nekonome, which means cat's eye, which is what I named it. My beautiful, beautiful scintillator. Alright, this has been Tom from anti-proton.com, and bye-bye.